Hello boys and girls, welcome to another edition of AP Environmental Science, brought to you by Mrs. Gabriel and textbook authors Freidland and Relia. The goals for this presentation will be to describe the formation of Earth, describe the distribution of critical elements on Earth, at least the ones that we extract from Earth for human use, and to define the theory of plate tectonics and discuss its link to environmental science. This is an HEV. A hybrid electric vehicle. Actually, it's a Toyota Prius. It uses lithium. By using an HEV, people reduce the amount of fossil fuels that we depend on. It's more efficient than combustion automobiles. The problem is that there are other environmental consequences of mining the element lithium. Toyota has produced over 1 million Priuses, and most of the lithium comes from China. So what is this? It's a lithium mine. It's in Bolivia. Lithium is used in high-performance batteries. It's also used for the Toyota Prius battery, and its deposits are, in addition to China, also in California, Australia, Bolivia, and Canada. But we can't get it easily. This limits the production of HEVs, and lithium is a non-renewable resource. Problem: we mine these elements by pumping acids into deep boreholes to dissolve the surrounding rock and then remove the resulting acid and mineral slurry. It's a type of surface mining. We'll get to that soon. Impacts of this mining include ground disturbance. Air and water react with other rock minerals such as sulfur. This causes acid mine drainage that flows over the land or in groundwater. This is a problem because it dissolves metals and other elements. Highly acidic environment is a human health hazard, and I'm talking about 2.5 or less of a pH. It alters habitat and causes erosion. So why is lithium only in some places and not in others? Well, many of Earth's resources were determined when the planet was formed, which was about 4.6 billion years ago. These resources are unevenly distributed, and they're all that we have. Remember, they're non-renewable. When the planet formed, elements separated into layers. Heavier elements such as iron sank towards Earth's center, and lighter elements, such as silica, floated toward the surface. And gases, which were even lighter, became part of the atmospheric layer. So you can see in this diagram, they're showing you the layers, where they are vertically in order from densest to least dense. And by vertically in order, I'm talking about something called the vertical zones or vertical zonation. The distinct vertical zones of Earth are shown in this slide, and the innermost zone is called the inner core. Its dense mass is made up of nickel and some iron, and these are really dark minerals. And they're metals. They're heavy. They're dense. The mantle is made up of molten rock or magma that circulates in convection cells, a lot like the atmosphere does. And then you have, and go ahead and look for this, the astenosphere. Find astenosphere. This is in the outer part of the mantle. It's ductile or flexible rock. Sometimes you'll hear the ductility or flexible rock because it's almost like it's kind of moving. Sometimes they'll be referring to that as a plastic. Don't ask. This is just what they do. So that outermost layer is very brittle. It is the lithosphere. It includes the solid upper mantle as well as the crust. The crust is the outermost layer of the lithosphere. So know your words. Please understand that these layers do overlap a little bit. The lithosphere is made up of several large and small plates. These plates move as a result of convection within the astenosphere. Remember, the astenosphere is that flexible, ductile part of the mantle. Feel free to pause the video so that you can really spend some time understanding this picture. These are the layers shown in relation to one another. Again, the vertical zonation. And it also shows, what I really like about this is the convection cell theory. So the convection, which is that circular movement shown by the yellow arrows, convection also happens when you're boiling water and pasta. So you boil your water, you see your pasta moving around. If you really pay attention to it, you'll see it moving kind of, circles. It, gets superheated at the bottom, and then it gets carried up by the water that's gotten so hot, and it moves up towards the surface of the pot of boiling water, where it cools again, and then it sinks. The surface of your boiling material moves around just like the plates of Earth's crust. So you'll also hear a term called natural capital. The Earth's crust is made up of, a mosaic of all these huge rigid plates. They're called tectonic plates, which move around in response to forces that happen in the mantle. What are these forces? Well, they're convection cells. Now we're looking at a diagram, similar ideas, just from a different point of view. I'd like you to start by following the red arrows. This is showing you convection, which I just showed you in the last slide with the yellow arrows. So if convection is kind of circular, then some places have heat and the mantle material rises. In other places, the material sinks, where it gets cooler, basically. It must be balanced. This figure shows how the impacts of Earth's surface, or how this impacts Earth's surface, or the crust. So look where the arrows rise. What type of Earth's surface features are found here? Yes, ridges. What do we see where the crust is dragged back toward the Earth's interior? Yes, trenches. These are also called subduction zones. Notice that the features to the left and the right of the plate boundaries. So the major features of Earth's crust and the upper mantle are shown here. Remember that the lithosphere, which is composed of the crust and the outermost mantle, is rigid and brittle, and the asthenosphere, which is that zone in the mantle, can be deformed and plasticky and ductile, and it happens because of heat and pressure. This is a similar picture depicting the surface processes related to tectonic forces. These tectonic events bring with them different minerals, which we mine. We mine for the minerals. The minerals are a result of this tectonic activity, and it's not easy to mine for these. There's cracks all over the lithosphere, and they're associated with earthquake activity and with volcanic activity. These cracks are the plate boundaries. How do we know? Because earthquakes and volcanoes have formed along where we think these cracks exist, and where these particular features that were in the last few slides were shown. So we get volcanic eruptions. They're more prominent along all these boundaries. We could be wrong about this. It's not like we have a drill that's able to dig all the way through to the other side of the Earth. We don't have the technology for that yet. So the thing is, nobody's actually proposed a more believable theory than this. But you could be the one. Evidence again, and if these pieces fit together, animals will be able to walk from South America to Africa. These are animals that would not be able to survive the long swim across the ocean that exists between these land masses today. So, the continents and oceans are on plates that move. But these plates and the convection cells beneath them move very, very slowly. If you study the geologic timeline showing Earth's history as a result of plate motion, you'll get an understanding of how things have moved and changed over time. Note that geologic time is reported in big eons. See where the word eon is? E-O-N. And then we move to smaller subsets of those eons called eras, and then even smaller time blocks, and those are called periods. So take a look at this and answer this question. What era and period did dinosaurs dominate the Earth? Mesozoic era, Jurassic period. What about humans? Cenozoic and Quaternary. Also notice that Earth's surface and atmosphere change over time. For example, the Atlantic Ocean didn't even separate from Africa until the Jurassic period. And this is just another schematic to help you understand and maybe remember the concept of geologic time to scale. That's what's important about this. Other things change Earth's surface features as a result of tectonic activity. For example, we have hot spots that form island volcanoes in the middle of plates. And as the plate moves, new magma cools into rock and forms new crust. The magma and lava ooze out and they solidify. And more oozes out and solidifies until a big island forms. As the plate moves, the island location changes. So the plate is moving, but not the hot spot where that weakness is in the Earth's crust. So these are the boundaries that were discussed in all the previous slides, and the most important thing to help you remember them is just the arrows. Everything else is common sense that comes along with that. So if you look at the divergent boundary, the arrows are moving apart. Well, if they're moving apart, then something must be oozing out of there. If the arrows are coming together, then either we're building mountains or something's going to be sucked under something else. And then if they're moving side by side, well, nothing's going to have to necessarily ooze out, and nothing's necessarily going to have to smush and create mountains or a big trench, deep trench. Just, there's a lot of rock grinding against each other. So these are our divergent, convergent, and transform boundaries. So you see that the arrows are coming together here from the uppermost mantle on one plate to the uppermost mantle of another plate, and one is getting sucked under the other, and on top of that is continental crust. So we see a little bit of subduction, but we also see continental crust smushing into continental crust. Well, one is not more dense than the other. So if one's not more dense than the other, then there's only one place to go, and that's up. And that's how we create mountain ranges. An example of those types of mountain ranges that form as a result of converging plate boundaries are the Himalaya Mountains, where India is moving towards the Indian plate, is moving towards the Asian plate. And this is still happening today, which is why the mountains in the Himalayas are hypothetically getting taller. And then we have an example here of the transform boundary, and that's where, remember, those arrows were just kind of moving side by side. There was nothing crashing. One plate was not crashing into another. One plate was not being separated or torn apart from another. Just moving side by side. And the most famous one is this San Andreas Fault that runs through California. It's a big headache for Californians. I would like to stand on the San Andreas Fault and have one foot on the North American plate and another foot on the Pacific plate and get my picture taken. I think that would be really cool. So we've already seen this. I recommend you pause the video here and just take some time remembering. Look at your key in this map. Remember a subduction zone and what type of boundary that is. And then find the subduction zones on this map. Remember where volcanoes are, what type of boundaries are you usually going to find them out. And look for patterns and trends in the map. And then notice in the dark purple the ring of fire. And the ring of fire is where there really is a very obvious pattern of earthquakes and volcanoes, and that's why it's called fire, because of the volcano part. So the movement of plates causes earthquakes and causes volcanic eruptions. So we know about volcanic eruptions, but earthquakes are also hazardous to humans. This is an example of, or a picture of, the capital in Haiti, Port-au-Prince, in 2010 from that very, very powerful earthquake that they had. Okay, so this is the end of Part 1, Chapter 8. Did you meet your goals? Can you describe the formation of Earth? Can you describe the distribution of elements on Earth that we extract from Earth for human use? And can you define the theory of plate tectonics and discuss its links to environmental science? If so, great. If not, please replay this presentation and reread the goals to determine if they've been met. I hope you learned enough to make our footprint on Earth smaller. Have a great day.